हेलो माय डियर मैकेनिकल चैंपियंस, हाउ आर यू ऑल? व्हाट्स अप? कैसे हैं सब लोग? अपन के में नाचेन. Please guys do join me fast, and those who are already here, please let me know through the comment section. Am I audible and visible to all of you? Can you guys hear me? This is Chandrasekhar welcoming you all to the India's largest, the best and your favorite live learning platform, that is Byjus Exam Prep. I hope everyone is safe and sound and having your preparation in the right direction with your full dedication, hard work and enthusiasm. So we are live here with the beautiful session for today, that is heat exchanger, one of the important topics of heat transfer subject. Actually, the heat transfer is divided into four major parts. Out of these four major parts, the three topics are the various modes of heat transfer. Conduction, which is lengthy topic, vast topic involving steady state conduction, unsteady state conduction, pin theory, critical radius of insulation and composite system along with combined modes. So the conduction is very vast syllabus. The second mode of heat transfer is convection, again very vast syllabus because of forced convection and natural convection involving the concept of fluid mechanics. And the radiation mode of heat transfer, another a lengthy topic. But let me tell you, the heat exchanger is very simple, very small topic, easy to understand and highly scoring in your GATE examination. The heat exchanger is one of the topic which is very simple and very short topic. It involves the two important methods of analysis. One is LMTD, another is NTU. Can you just let me know what is LMTD and what is NTU? Hi Sachin, good evening, welcome. How are you? What's up? So are you ready with your full preparation to explore this beauty of heat exchanger? We will be talking about we will be discussing some numericals, and during the numerical practice only we will discuss the related concept. If anybody is having any doubt, anything to ask in heat exchanger, you are most welcome to ask through the comment section. Yes, LMTD stands for logarithmic mean temperature difference. Why do we require LMTD in heat exchanger? In heat exchanger, actually there are two fluids. One is at higher temperature, that is called as hot fluid. Another is at lower temperature, that is the cold fluid. And there is an exchange of heat between these two fluids, and that is why the name is heat exchanger. So in the heat exchanger, the temperature difference between hot fluid and cold fluid is variable. So to make our analysis more simple, we define a temperature difference which is constant between the hot fluid and cold fluid, and that is called as logarithm. It is a logarithmic function, and that is why it is called as logarithmic mean temperature difference. And NTU stands for number of transfer units. It gives the information about the size of the heat exchanger or area of the heat exchanger. Even though NTU is unitless, but the value, the magnitude of NTU stands for the area of the heat exchanger. So lesser is the size, lesser is the area, more will be the economic performance of the heat exchanger. So LMTD should be as large as possible for better heat exchanger, and NTU should be as small as possible for better economic performance of the heat exchanger. कल का PDF पेंडिंग है क्या भव्या? Didn't I share in my Telegram group? अच्छा, I didn't share it. Okay, I will do it today. I think I have shared. What I feel is I shared it. Concept clear नहीं है सचिन? I will be there to help you out. जरूर भाव्या, definitely. This is my introduction for those who are meeting me for the first time, and you can always contact me through the mail ID which is there on the screen. And those who have not joined me on the Telegram yet, I would recommend all of you to be part of my Telegram group. because you will be able to discuss more when you become part of my Telegram group. All right. So you are watching me live through the GATE Rankers Monsoon series, which is running on the YouTube channel free of cost for all the GATE 2023 aspirants. We are discussing the numericals, and along with that, we are also discussing our related concept through the numericals, because the GATE is all about the numerical practice, and the learning is never done without practicing numericals, without making mistakes, without making errors, without making defects. So the more you practice on your own, the more you commit the mistakes, you improve your understanding better and better. And those who want to become the part of our paid courses, we are having the scholarship test on 24th of July, that is on Sunday at 11 a.m. You can register to the scholarship test, that is completely free, and based on your performance in the scholarship test, you will be able to avail the scholarship for our paid classes. All right. So let us start with the question. The first question on the screen. In a two fluid heat exchanger, I told you in the heat exchanger there are two fluids. One is at higher temperature, another is at lower temperature. One is called as hot fluid, another is called as cold fluid. And we are using the notation 1 for inlet point of the fluid, or entry of the fluid, that is 1, and suffix 2 will be used for outlet or exit of the fluid, outlet or exit. And small h will be for hot fluid. There are two fluids, one is hot fluid, and small c will be used for the cold fluid. Right? So in a two fluid heat exchanger, the inlet and outlet temperature of hot fluid are these. So we can say TH1, inlet temperature, 1 for inlet, H for hot fluid, is 65 degrees Celsius. TH2, outlet temperature of the hot fluid, is 40 degrees Celsius respectively. And for the cold fluid, these are 15. TC1, inlet temperature of the cold fluid, is 15 degrees Celsius, and TC2 is equal to 42 degrees Celsius. Hot fluid gives the heat to the cold fluid, so the hot fluid temperature decreases from inlet to outlet, and cold fluid is receiving the heat from the hot fluid. That is why temperature increases. So in the arrangement, hot fluid temperature of the hot fluid decreases and temperature of the cold fluid increases. That is how the heat exchanger works. Now, based on the temperature values, can we find out whether the heat exchanger is parallel flow or counter flow? Can we find it out whether it is counter flow or parallel flow heat exchanger? Yes. How to identify if you are comfortable with the temperature profile of the heat exchanger? How to draw the temperature profile? If you see, if for parallel flow heat exchanger, both the fluids are flowing parallel to each other and in the same direction. This is how the temperature versus area can be drawn for parallel flow heat exchanger. This is parallel flow. For parallel flow heat exchanger, the temperature versus area curve will be drawn like this. The hot fluid inlet temperature is TH1 and TH2 is the outlet temperature. This point represents TC1 and TC. Both are flowing parallel to each other and in the same direction. That is called as parallel flow. And symbol will be two parallel arrows. The symbol is two parallel arrows having the same direction. This is the parallel flow. So in case of parallel flow, what we can say, TC2 should always be less than equal to TH2. The cold fluid exit temperature cannot be more than the hot fluid exit temperature, because if the cold fluid exit temperature will be more, then what will happen? The heat will start flowing from the cold fluid to the hot fluid. That is the condition for the parallel flow heat exchanger. If we draw the temperature profile for the counter flow heat exchanger, one fluid is flowing in positive x direction, another fluid is flowing in negative x direction. So this is how the temperature profile will look like. TH1 is the inlet temperature of hot fluid and TH2 is exit temperature of the hot fluid. TC1 will be here and TC2 will be. So cold fluid temperature profile should always lie below the hot fluid temperature profile because the heat is always flowing from hot fluid to cold fluid. The cold fluid temperature profile cannot be lying above than the hot fluid temperature profile. That is the condition for a heat exchanger because heat always flow from high temperature to low temperature. Heat always flow from hot fluid to cold fluid, and that is why the hot fluid temperature should always be more than the cold fluid temperature at any point. So if you see from this condition, we can say TC2 should always be less than TH1, but TC2 can be less than, equal to, or greater than TH2. There is no connection between TH2 and TC2. TC2 can be less than TH2, TC2 can be equal to TH2, or TC2 can be greater than TH2. If you see TC2 and TH2, TC2 is greater than 42 is greater than 40 because TC2 is greater than TH2. So the only possibility, parallel flow possibility, is ruled out. This cannot be a parallel flow. So it can be counter flow. The exit temperature of cold fluid, if it is more than the exit temperature of the hot fluid, then it cannot be parallel flow heat exchanger. It can only be counter flow heat exchanger. The option is incorrect. Heat exchanger device with both parallel flow and counter flow operations are possible. No, it cannot be parallel flow and none of the above. B is the right answer. Yes, Bhavya. Yes, Bhavya, very nice. The cold fluid exit temperature can be more than the hot fluid exit temperature only in case of counter flow heat exchanger. It cannot be possible in case of parallel flow heat exchanger. All right. So that is how the answer to the question is option number B, counter flow. The next question on the screen. Is it clear, Sachin? The next one. For the same inlet and exit temperatures of the hot and cold fluid, it means for the same terminal temperatures, the logarithmic mean temperature difference is, for same terminal temperature, if TH1, TH2, TC1 and TC2 are constant. If the same terminal temperatures are there, then which one of them will have more LMTD and which will have less LMTD? Do you know that? In general, if the terminal temperatures are same, for same terminal temperatures, for the same terminal temperature, LMTD for counter will be more than LMTD for the complex heat exchanger. Complex means cross flow as well as multipass or shell and tube type. And the minimum value of LMTD will be for parallel flow heat exchanger. But if there is a phase change, now if there is a phase change for a condenser or evaporator, what is condenser? When hot fluid is undergoing a phase change, the hot fluid temperature remains constant. And what is evaporator? Evaporator is the heat exchanger when the cold fluid is undergoing a phase change. In case of evaporator or a condenser, the relative direction of the flow is not important as far as the thermal performance is concerned. So LMTD for counter flow condenser is same as LMTD for complex heat exchanger when there is a phase change is equal to LMTD for parallel flow heat exchanger. Yes, if there is a phase change in any of the fluids, the relative direction of the fluid flow becomes insignificant as far as the thermal performance is concerned. But because it is a general heat exchanger, there is no phase change. So can we say the LMTD will be greater for counter flow than the parallel and cross flow heat exchanger? Option B is the correct answer. Yes, Nora Fateh. Option B, Kameshwar. Very nice. Good. Option B is the right answer. But if it would have been condenser or evaporator, then option C would have been correct, right? So that you need to remember, you need to understand that whenever there is a phase change in any one of the fluid, the relative direction of the fluid flow becomes insignificant as far as their thermal performance is concerned. I hope it is clear to all of you. If anybody is having anything to ask, please do let me know. The question number 3 is on your screen. Question number 3, very simple warm-up question. We will gradually move to the difficult type of questions. In a heat exchanger, it is observed that delta T1 is equal to delta T2. What is delta T1 and what is delta T2? Delta T1 is the temperature difference between the two single phase fluid. Single phase means there is no phase change. Both the fluids are having same phase at one end, and delta T2 is at the other end. This is one end, this is other end. This is the area we are talking about. A is equal to 0 and this is temperature versus area. This is one end, this is another end. And delta T1 is equal to delta T2. Delta T1 is equal to delta T2 can only be possible in which? If we draw the temperature profile for parallel flow heat exchanger, this is how parallel flow heat exchanger looks like. This is the temperature profile for parallel flow. This is delta T1 and this is delta T2. So delta T1 cannot be equal to delta T2 for parallel flow. For parallel flow, it cannot be possible. If we draw a temperature profile for condenser, the hot fluid will be a horizontal line and cold fluid is a curve. This is condenser. So in condenser also delta T1 and delta T2 cannot be same. Condenser cannot be possible. If we draw the temperature profile for evaporator, in case of evaporator, cold fluid is undergoing a phase change, but hot fluid is a single phase. So this is delta T1 and this is delta T2. So in case of evaporator also delta T1 and delta T2 cannot be possible. If we draw the temperature profile for counterflow heat exchanger, if we draw the temperature profile for counterflow heat exchanger, then the counterflow is like this. So yes, there is a possibility that delta T1 and delta T2 are equal, isn't it? There is a possibility that delta T1 and delta T2 might be equal. That will be the special case of counterflow heat exchanger. And when delta T1 is equal to delta T2, do you know, if delta T1 is equal to delta T2, that means counterflow. And when this is the condition, then the temperature profile will become straight lines, two parallel and straight lines. Do you agree? Delta T1 and delta T2. The temperature profile will become straight lines. They will not be a curve. They will not be curved. They will become straight lines. Delta T1 is equal to delta T2. And the LMTD will be equal to, in such situation, this will be equal to LMTD. Do you get it? If you use the formula, you will not get anything. If you will use the formula for LMTD, you will get nothing. For a special case of counterflow heat exchanger where delta T1 and delta T2 are equal, then the temperature profile will be two parallel lines, parallel straight lines, and the LMTD will be the difference. LMTD is the mean temperature difference between hot fluid and cold fluid. Because they are two parallel lines, then the temperature difference between the hot fluid and cold fluid is already constant, and that is called as LMTD, right? Question number 4 on the screen. Question number 4. With answer Kameshwar, Nora, Bhavya, Sachin. It is a counterflow heat exchanger. You should underline this important fact. Is used to heat water from 20 to 80 degrees Celsius. The water is getting heated, so that is the cold fluid. The heating of the cold fluid is taking place in heat exchanger by using hot exhaust gases. That is the hot fluid. Hot fluid is the exhaust gases entering at 140 and leaving at 80 degrees. If we draw this counterflow heat exchanger, then the cold fluid is water entering at 20 degrees Celsius and leaving at 80 degrees Celsius, and the hot fluid is exhaust gases entering at 140 degrees Celsius and leaving at 80 degrees Celsius. Then the logarithmic mean temperature difference is, if you calculate delta T1, if you calculate delta T2, what is the formula for LMTD? For any heat exchanger LMTD is delta T1 minus delta T2 upon natural log of delta T1 by delta T2. That is the general expression for calculating LMTD, because it is involving the logarithmic function natural log. That is why it is called as logarithmic mean temperature difference between hot and cold. If you find out delta T1, what is delta T1? Delta T1 is equal to 140 minus 80. How much is that? 60 degrees Celsius. What is delta T2? Then it is 80 minus 20. That is also 60 degrees Celsius. So it is a special case, because delta T1 is equal to delta T2. It is the special case, and for the special case this formula is not going to work, because it will give you 0 by 0 form. If you put the values in the formula, you will get 0 by 0 form. So we use L'Hospital rule. What do we do? In such case we use L'Hospital rule. We use L'Hospital rule, and with this delta Tm mean temperature difference is nothing but delta T1 is delta T2. That will be 60 degrees Celsius. Option C is the correct answer. Option C is the one which is correct. Clear? So whenever there is a counterflow heat exchanger, you need to check first whether it is a special case or not. If you don't check whether it is a special case or not, and you will start putting the values in the formula, then you will get 0 by 0 form, and that will get you nothing. That is why you should always check for a counterflow heat exchanger. The next question is MSQ. The next one, let us solve the next question. There are two parts actually. You need to find out the LMTD and the surface area of the heat exchanger. Out of A and B, one option is correct. Out of C and D, another option is correct. So it becomes MSQ. So you need to find out the LMTD as well as the surface area. A double pipe. What is a double pipe? Double pipe is concentric tube type. So it can be counterflow or parallel flow. There are two concentric tubes. That is called as double pipe. Can be parallel flow or counterflow, but it is given as counterflow heat exchanger. Is to be designed to cool 12,000 kg per hour of an oil of a specific heat. This mass flow rate is given for the oil, and oil is the hot fluid. Why? Because it is cooling from 85 to 55 degrees Celsius. TH1 and TH2 are given. Specific heat CP is also given. By water, water is the cold fluid. Entering the heat exchanger as 30, that is TC1, and leaving at 45 degree, that is TC2. All the terminal temperature are given. If we draw the temperature profile, hot fluid is oil and cold fluid is water. 85 is the inlet temperature of the hot fluid, and 55 degrees Celsius is outlet temperature. And water is having the inlet temperature to be 30 degrees Celsius and 45 degrees Celsius temperature. If the overall heat transfer coefficient of the heat exchanger is 400, calculate the LMTD. For calculating the LMTD, we need all the terminal temperatures. For calculating LMTD, we need all. Yes, Rini. Yes. Whatever book you feel comfortable with, can use that book as the reference book. There is no harm in that, because the heat transfer topic remains same in each and every book. It is only the matter of concern that whether you like the way of presentation or not. If you like R.K. Rajput, if you are studying from R.K. Rajput, that is also fine. If you want to study from the foreign author like Sengel, that is also great. So there are a lot of books. What I recommend is Sengel. Why? The reason is because you can refer Sengel for heat transfer. You can refer the same author for fluid mechanics. You can refer Sengel for thermodynamics as well. So if you refer a single book for these three subjects, then you will be able to develop a connection between the concept of different subjects. Because so many times the GATE asks the question from multiple subjects. The single question involves the concept of multiple subjects. That is why if it is possible, refer Sanjal. It is well written, simple language, and very well explained. But if you like R.K. Rajput, then also it is not a problem. So for calculating LMTD, we'll require all the terminal temperature. Without knowing the terminal temperature, we cannot find out LMTD. LMTD will be equal to, because it is counterflow, so delta T1 85 minus 45 minus delta T2 50 minus 30, 55 minus 30 upon natural log of 85 minus 45 divided by 55 minus 30. What is LMTD? What is the LMTD you are getting? LMTD, this is delta T1 85 minus 45. That is delta T1, and delta T2 is 55 minus 30. LMTD will come out to be 31.9. Are you getting 31.9 degrees Celsius? Please give me thumbs up if you are getting 31.9. Option A is correct. For question number 5. Now the next part is surface area of the heat exchanger. Now if you write the heat transfer rate Q for a heat exchanger, that can be written as m dot h into ch into th1 minus th2. That is the heat loss by the hot fluid is equal to m dot cc into tc2 minus tc1. That is the heat gained by the cold fluid. That is the heat lost by the hot fluid. That is the change in internal energy of the hot fluid. That is the heat gained by the cold fluid. By cold fluid. Energy conservation equation. Heat lost by hot fluid is equal to heat gained by the cold fluid, and that will be equal to U into A into overall heat transfer coefficient, because it is having the combined modes of heat transfer, conduction as well as convection. So overall heat transfer coefficient into area of the heat exchanger into LMTD. That is LMTD. By using this expression, we can find the value of A. So U is given as, what is U given? U is given as overall heat transfer coefficient is given as 400 into area into 31.9 is equal to m dot c. We can use m dot ch also. The mass flow rate is, for hot fluid, it is 12,000 kg per second, and the specific heat 1.95. 12,000 kg per hour. It is kg per hour. So it will be 12,000 divided by 3600 into 1.95 into 10 to the power 3. You should put all the parameters in their SI unit into TH1 minus TH2. That is 85 minus 55 will give you the answer for A. Can you find out the value of A? Can you get the value of A? The area will come out to be 15.28. Are you getting 15.28? This will be the area. 31.9 is the LMTD. Yes, Sachin. But by using the energy conservation equation, this is our energy conservation equation, we can find out the area of the heat exchanger also, 15.28. Is this all clear to all of you? All fine? Kameshwar, Bhavya, Sachin getting 15.28. All right, so let us move to the next one. Question number 6. In a certain double pipe heat exchanger, double pipe means concentric tube type, hot water flows at the rate of 50,000. This is, water is the hot fluid. The mass flow rate is 50,000 kg per hour. You should take care of the unit. So you need to convert it into SI unit, that is kg per second, by dividing with 3,600. And gets cooled from 95 to 65, that is TH1 and TH2. At the same time, the same mass flow rate of cooling water, 50,000 kg per hour. Again, it is water. So we can say mass flow rate of hot fluid is same as mass flow rate of cold fluid. And Cp for hot fluid is also same as Cp for cold fluid. So the product of mass flow rate, m dot HCH is equal to m dot C. That is a special case. The product of mass flow rate and specific heat. Why the specific heat is same? Because the fluid is water. Both the fluids are water only. The cooling water enters at 30 degrees Celsius, that is TC1. The heat exchanger, the flow conditions are such that the overall heat transfer coefficient remain constant at this. This is U. Overall heat transfer coefficient, watt per meter square Kelvin. Calculate the heat transfer area required, assuming the two streams are in parallel flow, and for both streams, they are parallel flow heat exchanger. The diagram will look like this. Both are water having the same mass flow rate. If we talk about the hot fluid, the temperatures are 95 degrees Celsius and 65. That is the hot fluid temperature, and the cold fluid entry temperature is 30 degrees Celsius. We do not know TC2. To calculate LMTD, the area will be calculated from LMTD. So the first step is to calculate LMTD, and for that we need to TC2. So Q is equal to CH into delta TH is equal to C delta TC. That is energy conservation equation. Mass flow rate into specific heat of hot fluid is heat capacity rate. Mass flow rate and specific heat for cold fluid is heat capacity rate of cold fluid. Delta TH is TH1 minus TH2. Delta TC is TC2 minus TC1. Because these two are same, so we can say TH1 minus TH2 must be equal to H2 must be equal to TC2 minus TC2. From here we will get what is TH1, that is 95 minus TH2 65 is equal to TC2 is unknown minus TC1 is 30. From here we will be able to get TC first. What is the value of TC2? You will be getting TC2, that is 30 plus 30, 60 degrees Celsius is TC2. Once we get TC2, that is 60 degrees Celsius, then we can use the formula for LMTD, that is delta T1 minus delta T2 upon natural log of delta T1 by delta T2. That will give you the LMTD. So LMTD will be equal to delta T1 minus delta T2 upon natural log of delta T1 by delta. What is delta T1? That is 95 minus 30. 95 minus 30 minus what is delta T2? That is 65 minus 60. 65 minus 60 upon natural log of 95 minus 30 upon 65 minus 60. That will give you the value of LMTD. Can you do the calculation? Can you do the calculation? If you solve it, then LMTD should come out to be 23.39. Are you getting 23.39 degrees Celsius? That is LMTD for this heat exchanger. It is a parallel flow heat exchanger. And once you get LMTD, then Q is equal to U into A into delta Tm. That is LMTD. I am right using the notation delta Tm, mean temperature difference, is equal to, we can write CH into delta TH, or we can write C into delta TC. That is purely your choice. By equating these two, U is given as 2270 into area into 23.39 is equal to CH, that is the product of mass flow rate and specific heat. Product of mass flow rate and specific heat, 50,000 and 4.2. So 50,000 divided by 3600 into 4,200 into delta TH, that is 95 minus 65, will give you the unknown. Can you find it out? Are you guys getting 29? What is area? 32.96. Are you getting 32.96? Yes, Bhavya, 32.96 square. That is the area, 32.96. Close to 33. 33 meter square will be the answer. That is how the question will be solved in 3 steps. The first step is to find out the unknown temperature TC2, because for calculating LMTD, we need all the terminal temperatures. The second step is to calculate LMTD, and the third step is equating the heat transfer rate with UA into LMTD. Question number 7. Next one, question number 7. Very nice, Sachin. Good, good, good. Keep it up. Well done. Now solve the question number 7. If you have any doubt in theory portion, you are most welcome to ask me through the comment section. In a double pipe heat exchanger, counterflow heat exchanger, that is again very important whether it is parallel flow and counterflow. 1000 kg per hour of oil having a specific heat of 20 joule per kg Kelvin is cooled from, oil is the hot fluid, is cooling from 150 to 125 by the fluid. This is the mass flow rate of the cold fluid, specific heat is 16. The fluid leaves the heat exchanger at 75. That is the cold fluid. In such case, the temperature at which the cooling fluid is entering the heat exchanger and LMTD. Cooling fluid entering the heat exchanger, that is TC1 and LMTD. These are the two things. If we draw the counterflow heat exchanger, the temperature profile, temperature versus area for counterflow heat. The hot fluid is oil, cold fluid is not known. Cooling from 150 to 125, this is 150 degrees Celsius, this is 125 degrees Celsius. The cold fluid leaves the heat exchanger at 75 degrees Celsius, right? So TC1 is unknown. Without knowing TC1, we cannot find out the LMTD. So what we need to do is, we need to check whether it is a special case or not. Whenever you are having a counterflow heat exchanger, please check the product of mass flow rate and specific heat of hot fluid is coming out to be same as mass flow rate into specific heat of cold fluid, isn't it? Product of 1000 into 20 is coming out to be same as the product of 1250 into 16, isn't it? So it is a special case. And from the energy conservation equation, if the product of mass flow rate and specific heat are same, then delta TH is equal to delta TC, isn't it? Delta TH will be equal to delta TC because Q is equal to CH into delta TH is equal to CC into delta TC. That remains constant. From this, if delta TH is 150 minus 125, that is 25. So delta TH is 25 degrees Celsius is equal to TC 275 minus TC. Here we can find out the value. What is TC1? 75 minus 25, that is 50 degrees. Are you getting TC1 as 50? TC1 will come out to be 50 degrees Celsius. So the first value is for temperature. D cannot be true, A cannot be true. And because it is a special case, then we can find out LMTD. That is delta TM. 150 minus 75. So that LMTD will be 75. This is 50 degrees Celsius and LMTD will be 75. 50 and 75 are the correct answer. C is the right answer. 50 and 75. Yes, Sachin. Yes, Bhavya. Well done. What about others? Question number 8. Now it is your turn to solve this one. I want you guys to solve this question. Question number 8. In a double pipe heat exchanger, the cold fluid is water with inlet temperature 20 degrees Celsius. What is that? TC1 is 20. And mass flow rate, that is m.c, 20 kg per second. And the hot fluid is water. What is cold fluid? Cold fluid is also water and hot fluid is also water. So specific heat are same. That is 4.2. What is the inlet temperature? TH1, that is 80 degrees Celsius. And the mass flow rate, that is m.h, is equal to 10 kg per second, isn't it? Assume the Cp for water is 4.2. That is same for hot fluid and cold fluid, independent of temperature. What is the maximum temperature to which the cold fluid can be heated? What is the maximum temperature to which the cold fluid can be heated in a parallel flow as well as in a counterflow heat exchange? Can you let me know? If we talk about the parallel flow, let me do the parallel flow and you should do the counterflow. This is hot fluid, that is water, that is the cold fluid, that is also water. The inlet temperature of hot fluid is 80 degrees Celsius. The inlet temperature of cold fluid is 20 degrees. Right? Then, if we want the maximum temperature of cold fluid, do you agree the maximum temperature of cold fluid can be TH1? The maximum temperature of cold fluid, TC2 maximum. From here we can say TC2 is always less than TH2. For a parallel flow heat exchanger, the maximum value of TC2 can be equal to TH1, isn't it? If we write the energy conservation, that will give you Q maximum. So Q maximum is equal to CH into delta TH. So 80 minus TC2 maximum, that is TH1 is TC2 maximum, is equal to CC into TC2 maximum minus TC1. What is TC1? 20. That will give you the answer. Specific it will get cancelled out. It is only the mass flow rate of hot fluid into 80 minus TC2 maximum is equal to mass flow rate of cold fluid into TC2 maximum minus 2. What is the mass flow rate of hot fluid? That is 10. And the cold fluid is 20. If we put the value 10 into 80 minus TC2 maximum is equal to 20 into TC2 maximum, that will give you, what is the value of maximum TC2? For parallel flow, what is the answer? For parallel flow, it will be, are you getting 50? For parallel flow, are you getting 40? You will be getting 40 degrees Celsius, isn't it? Are you getting 40? So A and B cannot be correct. It is 40 in parallel flow. And what is the value in counter flow heat exchanger? What should be the value in counter flow heat exchanger? Have you understood the question? Have you understood the solution? In case of parallel flow, TC2 maximum can be TH1, and in that case Q will become maximum. When TC2 becomes equal to TH1, then Q will become maximum, because the temperature difference for the cold fluid will become maximum. Delta TC will become maximum. And for maximum delta TC, Q is maximum, that is equal to C delta TC. That is how it will give the maximum, and that is equal to heat loss by the hot fluid. Heat at all the points or in every situation, the total amount of heat loss by the hot fluid will be equal to total heat loss gained by the cold fluid. Counter flow का बताइए. Counter flow is a little complicated. If we talk about the counter flow को जरा देखिए. The temperature profile will be like this. It is all about the temperature profile which you understand. The hot fluid, this is the cold fluid. And inlet temperature of hot fluid is 80 and 20. This is 80 degrees Celsius and this is 20 degrees Celsius. This is TH2. Sorry, it should be not T. H2. TH2. TC2 maximum should be TH2 in parallel flow. In parallel flow, TC2 maximum is equal to TH2. ये होना चाहिए. काउंटर के लिए बता सकते हैं. This is all given. Now, if we find out what is the product of mass flow rate into specific heat for the hot fluid, the hot fluid mass flow rate is 10, the specific heat is same. So are you getting at the mass flow rate of cold fluid into specific heat? Specific heats are same because the mass flow rate of hot fluid is less than, so we can say CH is less than CC. The heat capacity rate of hot fluid is less than heat capacity because the mass flow rate of hot fluid is less than mass flow rate of cold fluid. and Cp of hot fluid is same as Cp for cold fluid. That is why the heat capacity rate of hot fluid is less than the heat capacity rate of cold fluid, or we can say delta Th is greater than delta Tc. Do you agree? So the profile will not look like this. The profile, how the profile will look like? How the profile will look like? Are you understanding it? We are calculating the heat capacity rate for the hot fluid and heat capacity rate for the cold fluid. What we are getting is the heat capacity rate for the hot fluid is less than the heat capacity rate for the cold fluid, because the mass flow rate of hot fluid is 2. This is 10 kg per second. Is it kg per second or kg per hour? 10. It is for hot fluid. It is 10 kg per second. It is 20 kg per second. Right? Specific heats are same. So the hot fluid temperature drop will be more than the cold fluid temperature rise, because the product of Th into delta Th is always equal to Cc into delta Tc. That is always correct. That should always be true. So the slope is, or the hot fluid temperature profile will have more slope and the cold fluid temperature profile will have less. Now if we want to find the maximum value of Tc2, then what we can have is, we can have the hot fluid temperature profile to be like this. Q should be maximum. For Tc2 to be maximum, what we can say, Q should be maximum, and for Q to be maximum, we can say this Th2 should be minimum. Th2 should be minimum, and the minimum value of Th2 is equal to T. That is the condition for Q maximum. In case of counterflow heat exchanger, Q will be maximum and Th2 will be equal to Tc1. That is equal to 20 degrees Celsius. We can write Q maximum as Th into delta Th, that is 80 minus Tc1, 20. I am writing Th2 minimum, that is 20, is equal to Cc into delta Tc, that is Tc2 maximum minus 20. And because the specific heats are same, so it will give you mass flow rate, that is 10 into 80 minus 20 is 60, is equal to 20 multiplied by, are you understanding it? Are you getting it? 20 multiplied by Tc2 maximum. That will give you the answer for Tc2 maximum. Is this clear to everyone? The answer will come out to be 30 plus 20, 50. Tc2 maximum will be 50. So it will be 50 for counterflow. Option C is the right answer. It will be 50 for counterflow. It will be 50 for counterflow, 40 for parallel flow. Right? If, look, if CH would have been more than Cc, if CH would have been more than Cc, then delta Th should have been less than delta Tc. In that case, hot fluid temperature profile would have been like this, and the cold fluid temperature profile would have been like this. Hot fluid entry temperature is 80 and cold fluid entry temperature is 20. In this case, if we want the maximum value of Tc2, then it should have been maximum as Th1. So Tc2 maximum should have been Th1, that is equal to 80 Celsius for Q to be maximum. For Q to be maximum. Right? For Q to be maximum, this would have been the condition. And then we could have equated Q maximum is equal to Ch into delta Th is equal to Tc into delta Tc. From here we could have calculated Tc. Right? But because Ch is less than Cc, so the answer will be 50 degrees Celsius. Is this clear to all of you? I hope it is clear to everyone. What is the answer to the next one? Question number 9. Very simple question. I have already discussed about this. for a heat exchanger, delta T max is the maximum temperature difference and the delta T minimum is the minimum temperature difference. What is delta T max? The maximum temperature difference is TH1 is the highest temperature in the heat exchanger and T1 is the lowest temperature in the heat exchanger. TH1 is the highest temperature in the heat exchanger and TH1 is the TC1 is the lowest. That is delta T max. And what is delta T minimum? That is TH2 minus TC2. These are the maximum and minimum temperature. TH1 is the highest and TC1 is the lowest temperature in the heat exchanger. Because TH1 decreases, TH decreases in the heat exchanger, the hot flue temperature decreases, TH decreases and TC. LMTD is the logarithm in temperature difference. C minimum and C maximum are the minimum and maximum heat capacity rates. The maximum possible heat transfer between the two fluids. If CH is less than CC, then Q maximum will be equal to CH into TH1 minus TC1. And if that is how we can find out if TC is less than CH, these are the heat capacity rate, then Q maximum is equal to TC into TH1 minus TC. That will be the expression. So general expression is TH1 minus TC1 is delta T maximum and TC or CH, what to use will be decided which is lesser. So Q maximum can be written as C minimum into delta T, where T minimum is the minimum value among CH and C. Are you getting it? That is how we can find out the maximum possible heat transfer rate between the two fluids. Option B is the right answer. Option B is option B. Question number 10, formula based is just the formula. What about question number 10? Saturated vapor is condensed. So it is the hot fluid undergoing a phase change. And if the hot fluid is undergoing a phase change, that is called as condenser. It is about a condenser. To saturated liquid in a condenser. Yes, it is the condenser. The heat capacity rate ratio. The heat capacity ratio is C minimum by C maximum, that is CR or C. The effectiveness of the condenser is, what is the answer? The effectiveness of the condenser will be option A is the formula for effectiveness for parallel flow heat exchanger. Option A is the formula for effectiveness for the parallel flow heat exchanger. 1 minus e to the power minus n 1 plus C upon 1 plus C. And option B is the effectiveness for counter flow heat exchanger. You must memorize these two formula. These are the formula for general heat exchanger. For parallel flow, 1 minus e to the power minus n 1 plus C upon 1 plus C. And for counter flow, 1 minus e to the power minus n 1 minus C upon 1 minus C into e to. There is a problem here. It is not correct. It is e to the power also. Let me make it correct. 1 minus C into e to the power. It should be e to the power. E to the power minus n. So let me write it. Press. Effectiveness for parallel flow is 1 minus e to the power minus 1 1 plus C upon 1 plus C. C is the, I am calling it as C. C is the heat capacity ratio. And effectiveness for counter is 1 minus e to the power minus n 1 minus C upon 1 minus C to the power minus n 1. These are the formula. These are the formula for general heat exchanger. Now for C is equal to 0. When do we have C is equal to 0? Either CH is infinite or CC is infinite. When CH or CC, any of them is infinite. So that means a condenser or evaporator. For a condenser or evaporator, C will be 0. C will be 0. When there is a phase change, Q is equal to CH into delta TH. If delta T or CC into delta TC, if delta TH is equal to 0, that means condenser. In case of condenser, CH can be called as infinite. And if delta TC is 0, that is evaporator. In that case, CC is infinite. So if any of these is infinite, then C will become 0. And for C is equal to 0, if we put C is equal to 0 in those formula, then effectiveness of parallel is equal to effectiveness for cross or complex is equal to effectiveness. Effectiveness will be same. Complex is equal to effectiveness for parallel. That will be 1 minus e to the power minus n. That is for C is equal to 0. For C is equal to 0, that will be the expression. It is C is equal to 0. It is the case of condenser means C is equal to 0. So the correct answer is option D. But for C is equal to 1, when CH is equal to CC or delta TH is equal to delta TC, in that case, for C is equal to 1, if we put the value C is equal to 1 in parallel flow, then you will get 1 minus e to the power minus 2n by 2. And for counter flow, you will get 0 by 0 form. So using the L hospital rule, it will be NTU upon NTU plus 1. That is for C is equal to 1 in case of counter flow heat exchanger if C is equal to 1. C is the option for C is equal to 1 when the heat exchanger is a counter flow. That is the special case that is calculated by using L hospital rule. This is the summary of a heat exchanger. These are the all formula you must memorize. L hospital rule. Is this clear? Option D will be the right answer. For this, it will be option D. Question number 11. Question number 11 on the screen. In a heat exchanger, inlet and outlet temperature of hot fluid are TH1 is equal to 220, TH2 is equal to 105 degrees Celsius. TC1, inlet and outlet temperature of cold fluid, 20 degrees Celsius, and T is equal to 90 degrees Celsius. So what is the effectiveness of the heat exchanger? Effectiveness is Q upon Q maximum. So effectiveness can be calculated Q actually CH into delta TH upon C minimum into TH1 minus TC1. That is the denominator I have already discussed. For delta T max. Or CC into delta TC also we can write C minimum into TH1 minus TC1. Or we can write U into A into delta Tm upon the denominator will remain same. That is how effectiveness can be calculated. Now the effectiveness of the heat exchanger. What is the correct answer? Now by reading the question, it looked like that it may be data insufficient because specific heat CH and CC are not known to us, not given to us. But try to understand what is delta TH. If you calculate delta TH, that is 115 degrees Celsius. And what is delta TC? 90 minus 20, that is 70 degrees Celsius. So do you agree delta TH is greater than delta TC? So we can say CH must be less than CC. So C minimum will be equal to CH. That is what we can find out from these temperatures. C minimum is CH. And if we use this formula, because CH is equal to C minimum, then effectiveness will be equal to CH up into delta TH, that is 115 divided by C minimum is also CH, then TH1 that is 220 minus TC1 that is 20. If you do the calculation, then it is 115 upon 200 will be the answer of effectiveness. Correct answer is B. Option B is the right answer. Option B will be the correct answer. 0.575. It cannot be 0.35 because the temperatures are given, so we can find out which temperature difference is more, whether for cold fluid or for hot fluid. Accordingly, we can find out which heat capacity is more, and we can find out the minimum value of C. Question number 12. The next one. Question number 12. In a concentric counterflow heat exchanger, water flows through the inner tube at 20 and leaves at 40. So this is the cold fluid. Water is the cold fluid, entering at 25 and leaving at 42. The engine oil, that is the hot fluid, enters at 100 and flows in annular flow passage. If we draw the temperature profile for counterflow, water is entering at 25 and leaving at 42. Hot fluid is entering at 100 that is oil, this is water, this is how the temperature profile will be drawn, and the exit temperature of the engine oil is also given, that is 50 degrees Celsius. The mass flow rate of water and engine oil are also given, mass flow rates are given, specific heat of water and oil are also given. The effectiveness of the heat exchanger. What is the effectiveness of the heat exchanger? So from the terminal temperature, we can find out what is delta TH. Delta TH is 100 minus 50, that is 50. What is delta TC? That is 42 minus 25, that is 25. So delta TH is greater than delta TC. So CH will be less than CC, or C minimum is equal to CS. The question is from the similar case. Effectiveness is TH into delta TH upon C minimum into TH1 minus T. C minimum and CH are getting cancelled out. So delta TH is 50 divided by TH1 minus T1, that is minus 70. 50 by 70, that is 2 by 3 will be the effectiveness. Effectiveness will be 2 by 3. 2 by 3. The answer will be. The next one, MSQ, we need to find out the area and NTU. A counterflow heat exchanger. Hi Subhadeep, good evening. You are late, but please do watch the recording and try to solve these questions. They are beautiful questions which will help you to improve your understanding about the heat exchanger. It is a counterflow heat exchanger is to heat air which is entering. Air is the cold fluid which is entering at 400 with a flow rate of 6 kg per second by the exhaust gas. This is the cold fluid, and exhaust gas is hot fluid. You should understand which is the hot fluid, which is the cold fluid. Entering at 800 and flow rate is this. The overall heat transfer coefficient is 100 U, and the outlet temperature of the air. It is a counterflow heat exchanger if we draw the temperature profile like this. Air is the cold fluid and gas is the hot fluid. Air is entering at 400 degrees Celsius and the mass flow rate is 6 kg per second, and exhaust gas is entering at 800 degrees Celsius and the mass flow rate is 4 kg per second. The overall heat transfer coefficient is given. The outlet temperature of air is TC2, 551.5 degrees. Specific heat at constant pressure for both air and exhaust gas can be taken as 1100. Calculate the heat transfer area and number of transfer units. So to find out the heat transfer area, we need LMTD. So for that we need to find out TH2. Can you find out TH2? How? TH into delta TH is equal to CC into delta TC. Energy conservation equation remains constant. So because the specific heats are same, it is the mass flow rate. So 4 into 800 minus TH2 will be equal to 6 into 551.5 minus 400. So first of all, we need to find out TH2. What is the value of TH2? Are you getting 572.7? TH2 is 572.7 degrees Celsius. Now, once we get that, then delta T1, delta T2, find out LMTD. That is delta T1 minus delta T2 upon natural log of delta T1 by delta T2. First step is to find out TH2, because without knowing the terminal temperature we cannot find out. Then the second step is to find out LMTD. This is LMTD. Formula for LMTD is delta T1 minus delta T2 upon natural log of delta T1 by delta T2. It is 800 minus 551.5 minus TH2, that is, we have already calculated TH2, that is 572.7 minus 400 divided by natural log of 800 minus 551.5 upon 572.7 minus 400. To calculate what is LMTD, LMTD will come out to be 208.33 degrees Celsius. Please do let me know if you are getting the LMTD matching with my value or not. And now when we get these, then we can use the analysis of the heat exchanger U into delta Tm is equal to Ch into delta Th or Cc into delta Tc. U is given as 1100 area, and delta T is equal to 208.33, and Ch is mass flow rate of hot fluid. What is the mass flow rate of the hot fluid? That is 4 and 800 minus 572.7. That will give you the area. So if you will calculate, the area will come out to be 47.99 meter square, something around 47.99 meter square. That will be the area. Area will be 47.99 meter square. And what is NTU? That is U into A by C minimum. That is NTU. And what is C minimum? CH or CC. The specific heat is same for both. So it is the mass flow rate will decide. So we can say Cc will be more than Ch. Cc is greater than Ch because m dot C is greater than m dot C. So U, that is 1100 into 47.99 upon 4 into 100. That will give you the NTU. It is unitless quantity. NTU will come out to be 1.09. Isn't it? Once you get NTU, you can also find out, using these values, you can also find out the effectiveness. Isn't it? What will be the effectiveness? So the correct answer is B and C. Correct answer is B and C. And if we want to find out the effectiveness, because it is a counterflow heat exchanger, if you want to find out the effectiveness, 1 minus e to the power minus n, 1 minus c upon 1 minus c or minus n 1. That will give you the C is equal to C minimum by C. That is how we can find out the effectiveness for this. Right? So that is all from my side. This is your assignment question. Let me give you the answer also. B and D are the correct answer for this. Please try to solve these assignment question, and tomorrow I will be back at 6 p.m. sorry, and we will discuss the questions and the concept of the radiation shape factor. And day after tomorrow we will be having another session for radiation analysis that will complete our practice session for heat transfer. All right, so that is all from my side. See you tomorrow. Till then, enjoy, take care, have a good day, and please do share the link of this session to all your friends, and do like this session so that it reaches to all the mechanical engineering aspirants who are preparing for GATE 20. With this note, let me take your leave. Stay safe, stay motivated, and keep preparing. Thank you very much.